So let's do a quick thought experiment and imagine we wanted to power my entire home campus at Caltech. So we need to produce about 15 megawatts of power. And the standard approach today would be to use large horizontal axis wind turbines. Now these are a marvel of modern engineering with over 8,000 components each. And with just about a dozen of them at a good windy site, we could produce that energy. But there's a problem. The turbines at the front of the array create turbulence that reduces the performance and the lifetime of all of the other wind turbines and ultimately increases the energy or the cost of the energy that's produced. Now today the best solution we have is simply to make the turbines larger and spread them out as far as we can. But if we go back to that thought experiment, it means those 12 turbines are now sitting up at 300 feet and spread out over around 1,200 acres. Now, it's true you might be able to use the land in between for something like agriculture, but the big problem here is that over those 1,200 acres, the wind is not going to be uniformly strong. So inevitably, some of your turbines are in lower wind conditions, producing less energy, and that increases the cost of energy. But there's some other problems as well. And they all point to this issue of bigger is better, whether that's true. The cost of the engineering, the logistics of installation and maintenance, resistance due to potential impacts on the landscape and environment, and also access in the developing world, where many countries simply don't have the infrastructure to deal with such large machines. So for this reason, we decided to turn the problem on its head, so to speak, and that initial equation we flip with the idea of simpler and smaller vertical axis wind turbines that would be used in very large numbers. As you can see in our example here, the total number of components you're manufacturing doesn't change. But since we're only manufacturing about 12 different parts, we can take advantage of mass production even for small energy projects. Now, what do we do about that turbulence issue? And what do we do about the fact that these turbines are only at 30 feet above the ground? How do they get enough energy? Well, it turns out that fish have already solved this problem for us. Fish schooling in the ocean create wakes that are very similar to the wake of a vertical axis wind turbine. And so we designed wind farms that take our cue from nature and are bio-inspired. Here you can see our field site in California where we've been testing the idea over the past 4 years. We've taken about several thousand hours of data now on these different configurations, and it turns out it works. So on this next slide here, you're going to see the power produced at our site as a function of wind speed. You can see current technology in the gray band at the bottom and the performance of these bio-inspired wind farms. And as you can see, we can do up to a factor of 10 better. What that means for our thought experiment is we can reduce both the height and the size of these wind farms by a factor of 10. And in turn, we can solve all of those problems I described before with a technology that's smaller, simpler, scalable, and also safer for wildlife. Now, there's still lots of work to be done, but we're excited about a technology that could achieve cost-competitive wind power without the need for government subsidies. I'm John DeBerry, and you can learn more at our website. Thank you.